Hello and welcome to Iron Beetle, a show where we discuss exciting modern database implemented in C++ called DuckDB. That's going to be a different podcast. Here we are discussing TargetBeetle, which, unlike DuckDB, is a database which is aimed at online transaction processing. So the problem we are solving here is that we have a stream of business transactions. Someone sends some money, some goods, whatever, to another person, to another entity, and we want to record all these transactions as fast as possible, and we want to ensure all the endurance, like, that you don't double spend your money, that you don't order the same unique painting twice, there's some stuff. Why are we doing this? Well, because TargetBeetle, by being implemented from scratch with our bare hands, actually is pretty decent code base to learn how you do this. So the point here is not to advertise TargetBeetle and prove that it's better than any other database, but no. The point is just we are going to learn how to build these kinds of systems. And last time we looked at the part of the networking protocol for TargetBeetle, and specifically for Rodent. So let's recall what we were discussing last time, and I guess I want to share my screen, remove distractions from the screen, and go back to this picture. So we have our TargetBeetle cluster of 6 replicas. And our job is to replicate prepare, which originated on the primary, across the entire cluster. We kind of discussed a couple of ways to do this. We discussed star replication, where primary broadcasts to everyone, and that's not great because it means that the primary has significantly higher bandwidth requirements than every other node. We discussed ring replication, where the primary sends to the first backup sends to the second backup sends to the third backup, and we discovered that the drawback of that scheme is that if any prepare is getting lost, then your entire replication breaks down. So a single failure will require you to do a retry, and retries are bad because they introduce bimodality. So what we ended up with is that our actual replication path is going to be kind of like a ring, but with a primary in the middle. So, okay, this is very, very laggy. Basically, okay, no, I don't like this illustration at all. Okay, why is it so horribly slow? It used to be normal a while ago. So we have a primary, and the primary is going to send its prepare to two other backups. And because we are sending two prepares at the same time, even if one of them is getting lost, the second one will be delivered. And those backups will continue sending messages along this ring. And because we have 6 replicas in total, like one branch will be 3 backups and another will be 2. So this is like our topology which we arrived at, which kind of like balances the robustness of star replication and even utilization of network resources of ring replication. Furthermore, our idea is that we are going to dynamically switch which particular order are we going to send prepares to replicas in dynamically at runtime. So we pick like one fork, measure how well it performs, then we pick another fork, measure how that one performs, and select a better one, and then at some point later we repeat the experiment. So last time we covered this whole thing in a lot more detail, so if you are interested in theoretical description of the algorithm with pictures, then please check the last episode, because today we are going to dive into the implementation. So, okay, let's go and start this. So we are in our middle. We aren't going to blind you completely. And we'll go to the Rodent. So rodent.zig is a file which implements this adaptive routing idea. Okay, and let's see like how it works. So first of all, Rodent is a Zig struct. So our replica is going to hold an instance of Rodent, which the replica will use to figure out, when we need to send who we need to send a message. So in replica, when we are replicating a message, we go to the Rodent and ask it, hey, what is the next target? And then, as we described, we could send to 1 or 2 replicas. This might return 1 or 2, well, 1 or 2 replicas. So we iterate all of them and we send a message to every replica. Okay, so what are we going to need here? Well, obviously we need to know our own replica number. We need to know how many replicas are there in the cluster. We need to know how many are there standbys in the cluster. So as a reminder, standby, and this is kind of like part I'm feeling ashamed about because it's kind of it was supposed to be part of reconfiguration, but I didn't end up finishing the configuration work, only added standbys, and they've been in the code base for a couple of years. yeah, so should fix it at some point. But basically, standby is a replica which processes every transaction, so it has the same state as normal replicas, but it doesn't actually participate in the consensus protocol. Okay, then we obviously need to know view, which is required because we need to know who is the primary, because remember, our roads are kind of like forks which are anchored at the primary, so view is important. And finally, we have two roads. So road A is the road which we currently use. And the cost is how we feel about the performance of this route, how efficient it is. And then, as a reminder, we kind of like run these experiments, which gives us a better alternative, candidate B. And the idea here is that over time you converge to an optimal road, and like you're using this like road A, but you also maintain a second alternative, road B, and like you keep like the second best possible road. And if at some point road A becomes worse, like a replica crashes and the latency numbers for road A start to shoot up, you actually have a candidate road B which you can switch to. Okay. And finally, we say that we'll dedicate 5% of our ops, so 1 in 20, to experimental roads. Okay, and finally, we are holding op history. And what is op history? Okay, so it is certain number of ops, which is prepare pipeline Q max, which says, okay, now I got it. And again, this is kind of embarrassing because this is the code I wrote and I completely forgot everything about it. So yeah, like that's kind of like the thing. Like as a programmer, you shouldn't. Let me try to let a little bit more light in here. As a programmer, you shouldn't really optimize for remembering the code, because over time you will write a ton of stuff, and it's just like infeasible to remember like moderately large programs, even if you wrote everything yourself. Like you will forget. What you want to optimize for is your ability to jump back into the code to understand it again, because like every time I open the code, which was even written by me, I'm kind of like learning again. So, okay, this like road has to do with code. So how are we going to compute the cost of the road? And as we discussed previously, we want to use outcome-focused measure. So rather than, say, measuring ping round-trip times between replicas and inferring the cost of road from that, we actually do like a very direct thing. Like we use Rodent for replication. So the cost of the road is essentially the time for replication to be complete. But the problem is our consensus is pipelined. So it's not that like, we replicate one op, we commit it, and we replicate the next op, etc., etc. No, we actually are replicating a bunch of ops concurrently. So before we learn how long it took us to replicate op number 10, we might already have ops number 11, 12, 14 in flight. So, and what is replication? Replication is when you get prepare OK responses from the backups. So essentially, that means that for every op which is currently replicating, we need to maintain a bit set which says which replicas have acknowledged this op together with the time when an op was acknowledged by a particular replica. And once we have an op replicated across everyone, we could see like what was the last replica to acknowledge the op and use that to infer the cost of a road. So that is the history. For a certain number of recent ops, we track like who and when acknowledge those. So we see like we store op number, we store a moment in time when we prepared this operation, and then for every replica, we store moment in time when we received corresponding prepare okay. And yeah, presumably we track bit set of whom we received prepare okay from. Okay. And while we are at it, I actually want to immediately start refactoring this code. Because like we're using this bounded array type for road, and Zig is removing bounded array, and in general, I'm kind of like not really a huge fan of bounded arrays. I think like, you know, almost always, if you're using a bounded array, it's better to open code it. Because this road probably is going to have some extra APIs. So I actually want to do this right here. I actually want to try to go and replicate it. So our road counts replicas max. Each replica is an U8, and it's undefined. Well, maybe not undefined. Okay. And then there is count, like how many replicas are actually in this road. Again, maybe actually we don't need this count. Well, we'll see. Okay, let's set up compilation here just so that we could get errors and fix them as we go. Okay, yeah, a bunch of errors. Okay, this is good. Okay, so with that in mind, let's continue reading. So what exactly is the history? We kind of like describe it. I guess this could be just an empty history. Wow. Const root history equals. Could simplify this a bit. Okay, and the history has a record prepare op function for when we receive an OK from a particular replica. So, okay, we compute how long. So this is like when we originally created prepare OK, and this is the duration until prepare OK. I remember actually originally started using a U64 and U64 here, and well, obviously that quickly led me to confusing those two and making a bug. So I'm kind of like unsure just how hard you should go towards typing everything, but I do strongly feel that you need to make a distinction in types between a type which specifies moment in time and a type which specifies duration. This is like very easy bug to make. Okay, so this is a latency for our prepare OK. If we already had heard from this replica, well, we can double check that we heard from that before. Oh, actually, you see also like nice pattern here. Like in general, like we need to deal with time here. Like we need to know like what is that, and like the most generic way to inject time is to say, okay, this thing has access to the clock, like ejected as a dependency, and the clock has method now which returns time. But actually, it is not that often that you need a generic access to the clock, which you could use multiple times. Like usually you only need access to only a single timestamp, which is now. So instead of parameterizing the whole thing by the clock, I'm going to pass this now as a simple instant as an argument. Okay, so if we already received repair okay, then we should have high latency. Otherwise, we check that it is indeed not received, and then we say, okay, this is what our latency is, and I have this latency max context because one thing we are going to do with these latencies is that we are going to add them up, because one metric which we care about is like how long did it took us to replicate this to everyone. So we want to minimize the total sum of all the latencies from all the replicas, and that means that we need to sum the latencies up. But that means that we need to guarantee that latencies are bounded, that we wouldn't get overflow. And well, we'll just say that, hey, we have this maximum latency, which is like 10 hours, and we just forcefully cap everything to 10 hours. Okay, so that is balance. Now, what is the cost? Well, the cost is actually interesting. The cost is actually three-dimensional. So imagine like you have this like history for an op. So you know for each replica when you receive repair okay, essentially like 6 numbers. How do you measure those 6 numbers? Well, kind of like the well, you could, you know, imagine various ways how you could measure them. You could take a median, take the maximum, take the sum, or like maybe some other function. And it's curious that actually you care about all of those. So, okay, what is the thing we care about most? Well, the thing we care about most is how long did it take us to replicate the prepare to a sufficient number of replicas such that we can execute the iteration. And recall that we use 6 replicas in a cluster and flexible quorums. So that means that we need 3 replicas to replicate it. And that means that we care a great deal about the first 3 latencies, because they determine when we could actually execute the operation and respond to the client. And we don't really care all that much about the latencies after the first 3. And also, for the first 3, we only actually care about the slowest. So we care about the slowest of the 3 fastest replicas. And that is exactly median. So median is like what we care about most. But okay, after we replicate it to 3 out of 6, we still want to replicate to everyone else to make sure that if one of that 3 fails, then we could quickly like replace it. And again, so like another metric we care about is yeah, like what is like the largest latency to replicate. Moreover, like you could mention that depending on a network topology, like replication might not actually reach every single replica. So some replicas might be unreachable, and those replicas will get latency max. So like another thing you could binary care about is whether you replicate it to everyone or only to a subset of replicas. Like maybe some prepare like just doesn't reach everyone. And here, this maximum also captures this. So if maximum is less than 10 hours, then you know that you replicated to everyone. If maximum is 10 hours, you know that, hey, yeah, actually we didn't reach everyone. Finally, even if your median and the maximum is the same, you also care about the total sum of the latencies. Because in general, like the latency to send prepare from node A to node B roughly corresponds to the cost of the network. Because like on a fast and cheap network with like high bandwidth, you expect replication to be very fast, but on a slow last mile network, which is built by kilobyte, you expect like your latency to be larger. So we want, like, in addition to minimizing the tail latency, we also want to minimize all the latencies between. So that's why we do the sum here. Okay, so this is how we why don't you want to fold this comment? Okay, we will take a look at this comment, but like first I want to look at the code. So this is how we compare two costs. We compare them in this order: median, maximum, sum, and we only consider cost to be less than other costs if it is significantly less, because again, this is like all network, this is all fuzzy and laggy, and we kind of don't really want to switch our road if this is only a marginal improvement. So our improvement here is 10% for median and the maximum, and 5% for a sum. So we basically check that particular field of the left coast is less than the right coast, even if we multiply left-hand side by the threshold. And this is again where we care about being sufficiently far from U64 max, so we could multiply by 20. And the thing here is that you really want to look for as low as 5% improvement. And this is example. So let's assume that the replicas are actually on a physical ring. And the path, the cost for transferring between two replicas is proportional to the distance between replicas. So sending from the primary to 1 or sending from 4 to 3 costs you 1. But sending from the primary to 2 costs you 2 because you need to do 2 hops. Okay, so what is the overall cost of this path? Well, primary needs to send to 1 and 5. This is 2. And then 1 needs to send to 2. 5 needs to send to 4. and 4 needs to send to 3. So it's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. But remember that like we only learn about something being replicated when the primary receives prepare OK back. So we care not only about the latency to send prepare, but also about the latency to get prepare OK back. And for prepare OK, latency is actually higher for this topology. So when 1 sends prepare OK back to primary, it's 1, but when 2 sends prepare OK back to primary, it's 2. And it is free for 3. Okay, it's kind of like horrible choice of replicators, but anyway. So our total sum of latencies is going to be 14. So this is the next best path, where from 5 we send to 3, and from 3 to 4, rather than like actual ring. So here, because of this extra lag, the cost of prepares is going by 1. But the cost for prepare OKs stays the same. So here, our cost is 15. And the best cost is 14. So the difference between the best and the next best is less than 10% and more than 5%. Okay, that's it. Okay, then we obviously don't want to compute cost based only on single prepare, because, well, like, things happen. Maybe we weren't lucky. And remember that we actually maintain 2 costs for route A, so the route which we are currently using, and the route B, like the experimental thing which might or might not be better. The way we maintain the cost for them is different. So for route A, what we do is that we do exponential weighted moving average, which basically means that we average costs across all the ops which use this route, but we weigh more recent ops more heavily. For route B, for experimental route, well, I kind of haven't told you yet because we haven't seen this in code, but what we'll actually do is that we will run every experiment twice. So we'll take 2 subsequent iterations and we'll use the experimental B route for both of them. So for route B, it's going to be just simple average. Okay, so that is how it is expressed in the code. So the average is, well, simple average. And again, like, we very much care that we are not overflowing here. And for exponential weighted moving average, we compute that with 4 thief like ratio. So we take 4 times the current sum, and then we take the new sum, and then we divide everything by 5. Okay, so seems relatively straightforward. Okay, so let me also show you this like nice pattern. Like this is how I think you should lay out your Z code. So first you do the fields, then you do the types, then you do like self-alias. You say, okay, this thing is Rodent, and then you go with methods which you start with any, because you really do want fields to be before the types, because the fields tell you the state. And as Fred Brooks told us, state is where all the condensed logic of the system resides. Like, you don't really want to look at the code, you want to look at the state. Okay, so Nothing interesting here. We just configure the routing with number of replicas, number of state bytes, and the current replica, running sanity check. Well, I guess this is it. There is something interesting here in that we need to compute some route. And we need we need to start with some route, and we do this default view. And okay, so I guess this is where we can remember that we are actually introduce the route here, so we could say view default, and let's call this result. Okay. Replica 08 void. We want to assert that count is less than, for instance, replicas max, and we want to see road replicas road count is equal to replica, and road count plus equal 1. Okay, so this is like 3 lines is the entirety of what a bounded array actually brings us. So how do we take default view? Well, we just say that our road is 0, 1, 2, 3, 4, 5. And then we rotate the correspondent slice result replicas midpoint equal primary index. So okay, let's say that our view is 2. So we start with 0, 1, 2, 3, 4, 5, and then we rotate it to be 2, 3, 4, 5, 0, 1. Which makes me think, like, why are we representing that way? I wonder if we actually should go from the opposite directions, maybe. Because what we actually want to represent here is the road 2, 3, 4, 5, and the road 2, 0, 1 to 1, 0 rather. And actually, I wonder if we have a bug there. Well, never mind. So because it kind of I kind of want to be like gap there, like, you know, in the middle of this replicas array. But well, we'll see. Maybe that is a bad idea. Okay, so rotate the primary. Oh, actually, okay. Actually, I kind of lied to you. What I drew here is the primary being in the middle, and it is actually like for view 2, it is already in the middle. So let's say we want to do this for view 5. So actually for view 5, we want this to be 3, 4, 5, 1, 0, 2. Okay, so this, okay, yeah, actually, okay, I like this. I like this representation. So we always have the invariant, like the primary is in the middle. Okay, so when we initialize That means that we want route view default. Okay, for view 0, so that means is 1, 2, 3, 4, 5. What we'll actually do is 4, 5, 1, 2, 3. Okay. Okay. Poland still doesn't work the way I wanted to, sadly. Okay. View change. So we realized that, hey, we now have a new view. And the primary is different, and probably we are changing the view because something's wrong in our network topology. So it would be like first impossible to reuse existing route because the primary is in a different place. Like we want to at minimum to rotate our fork, but also maybe we are changing the view because our previous fork is not working. So we need to reset view to something, and we reset it to view default for this new replica. And I guess valid. Do I want to? Well, okay. Let's go all the way there, and then optimize. So valid u32 replica count u8. We actually want to assert that the result is valid for view and replica count. Okay, if it's not equal to replica count, we return false. If replicas count, if any replica is greater than replica count, return false. We also return false if any two different and we check that the replicas, it's not primary index, it's just like primary. Oh, we have primary. Okay. Can we write this better? Primary index, primary index. Okay. Well, that's fine. Okay. So view change. We set our road to default view road in replica count. And we initialize both our main route and our alternative route as this route, and we check that the history is empty, because again, we are changing the primary, so the old history doesn't really make sense. Okay, route view default is what we've moved to route again. Okay, then for experiments, we'll have to be able to create a random route. And for that, we'll need a random number generator. Okay, so we put this undefined and 0. What do we do here? Okay. Trivial count. I wonder if actually we should not even care about replica count and just always initialize this to like 0, 1, 2, 3, 4, 5, 6, irrespective of count. Well, I think. Oh, okay, let's actually be like explicit here. So okay, we initialize to, well, we do initialize this to undefined, so everything else is set to undefined. So I was thinking like maybe we should do for replica count constants, replicas max, you know how to set a result push, something like unreasonable, like AA. But I think that's already what we are going to do from this undefined. Okay, so we start the trivial route, and then we rotate primary to midpoint. And okay, and the same here. We start with like trivial, and then we shuffle it, and we. I wonder, like, do we need to do this? Like, because I'm kind of like rotate primary. Okay, let's go maximum and rotate. Well, no. I was thinking like maybe we could like remove code duplication here, because what we want to do here and here is to rotate primary in the middle. But here we actually do want to properly rotate this primary, while here, because everything is shuffled anyway, we could just swap it. But I think it's fine. Let's keep it different. Okay, so but we actually do want to assert that the result is valid. Result. Well, okay. Now let's call this root. I actually like calling this root, not result. Okay. So, but here we could actually just directly replicas. Primary index midpoint. Okay, let's actually midpoint. Let's do align these. Are we using midpoint anywhere? Midpoint. And when we assert that something is valid, okay, so let's midpoint. Okay, that's better now. Now we use exactly the same code everywhere. Okay, so yeah, we now can create a random root, which is a fork. So which means that, like, just like a random permutation of our replicas, but just with the primary sitting at the midpoint. And we could use that for experiments. Okay, I guess, replicas count. Count. Okay, this is kind of like okay. Maybe we need. Well, no, this was better like that. Okay. So view change encode. So this one, I think we actually want to keep as a method of Rodent. Well, do we? Oh no. Okay, let's go maximally structured. Okay, random valid push. Okay, then we have encode and count. Replicas. So what does Rodent encode? So when we figure out that one road is better, so we run our experiments and we understand that hey, actually like this road is better, we want to communicate this to other nodes. The way we do this is that we encode road into a pin message. We basically include this as a number, and like, well, how would you actually encode the road? And turns out because we only have 6 replicas in the cluster, you could encode road very compactly as just a number. So if I'm reading this code correctly, we just encode each replica as a byte, and we pad the rest with FFs basically. And I'm wondering if we actually should have used this for like our original road representation. Well, maybe not, because it is convenient to use slices there. Okay. I'm wondering if we actually should just set FFs there, and then it could be simplified. Well, doesn't really matter. Okay. Yeah. So because this is road, it doesn't have to be road encode. So now our actual road encode is going to assert that road is valid for, well, we don't actually need replica count here. Well, no, we do need replica count because, well, maybe it was a different road. So we check that road is valid for Rodent view and Rodent replica count, and then we say that code equals Rodent code, and then we assert that the code is not 0. Okay. We have a nice test here where we actually just go and test every single road here. And well, I guess here we will replicate find count 0. Actually, can we? Okay, let's trivial. Can we like write kind of shuffle here more compactly? Trivial replica count. Random also replica count. So and then so how do we want to write kind of shuffle? well, we have this here. So we want to, for zero to replica count -1, I want to say that do I have range inclusive there and inclusive? Actually, I think I could use actually I think I could use index here. So wow, I'm using the index of the different array, so that doesn't work. Okay, so I want to say I plus, well, let's just write range inclusive. Replica count -1. Replica count. And let's see how we do range inclusive. So for our, this is fun, by the way. This is kind of like what if this exhaustive GAN thing? Oh, I think I would need another. Okay, so we are out of time. But I do want to cover exhaustive GAN at some point. So and then I want to swap. Well, I mean, like, why are we doing this? Why we are running shuffle? If we actually could, like, just write shuffle here, right? Okay, so we do shuffle replicas count. We don't need pool. Like, it's much simpler. Okay, and we do Rodent encode, Rodent decode, and that works. Okay. Well, okay. Let's see. Replicas count. Replicas decoded count. Okay, yeah, I love this better. Now let's do the same thing for rote decode, shall we? Okay, I positively do love how we introduce this thing here. Okay. So replicas. So code. View. Okay. Let's see. So we go extract byte from the code. And we check that if a byte is blank, it must be blank. So if it's not blank, we return null. So, okay. And otherwise, we check that the replica numbers are actually valid. Okay, and if route valid, view replica count, we return null. Otherwise, we return route. So this is kind of like very nice protected. Okay, route decode test. Oh, but I think we still want to have this public route decode, right? Route decode. Because again, this is the public interface of the Rodent itself. And the way this is going to work is that we are going to just return route decode, and we pass code Rodent view Rodent replica count. Okay, now for the decode, so for the encode, we test positive space. We go through every possible route and encode it and decode it, checking that the result is idempotent. For decode, we actually go for a negative test. Because so decode is trickier function than encode, because encode assumes that the input is valid and produces valid output. For decode, we want to produce valid output for valid input, but for the invalid input, we actually want to return null. So we want to check that it doesn't crash. So we essentially encode random route using bytes which are kind of like reminiscent of the bytes we might have. And then we check that if this thing decodes, then what it decodes to can be encoded to the same code. And then we asserted our test tests obviously a lot of invalid routes, but also some amount of valid routes. Actually, it should also test that invalid valid count, invalid count, because I mean invalid count. We want to assert that this is at least 100K, and we want to valid count plus invalid count equals to 200K. Okay, just to make sure that not all the routes are valid. Okay. Huh. Okay, so I feel like, huh, uh, I've overestimated my power. I was hoping that, like, we'll be able to go through implementation in one sitting and also explain how it is tested, and also refactor the roads, but we've only covered, I don't know, maybe 1/3 of what I wanted. Well, as always. Okay, so but I don't want to like make this episode super long because I actually want to do more episodes. So let's pause here. We're kind of like in the middle of refactor, but that means that, like, next time at 5 p.m. UTC on Thursday next week, we'll be able to jump right into the code, skipping all the intro, and like continue our refactoring / reading of the Rodent code. But I think we kind of like understand a little bit of the big picture here. Like, we see that, hey, this is just a single file. So all the adaptive replication Rodent is nicely encapsulated. And we maintain some state. So we maintain the active road, we maintain the experimental road, we maintain the history of operations for each road. So when we received a road, we know what the cost is, median, maximum, and sum of the latencies, which naturally corresponds to the time to commit something, the time to replicate fully, and the kind of like cost of a particular replication route, total cost of byte transfers, let's call it that way. And we kind of like started to see how we do like the basic stuff with the roads. So like default road for the view, road encoding, road decoding, testing a little bit, like, skipping that exhaustive thing. But as we haven't really got to the meat of the thing, which is next hope for the route. Like, how do we go to the next replica? And like this actual logic for running experiments and tracking statistics. But, well, that is for the next time. See you in exactly 1 week minus 1 hour and 15 minutes. Goodbye.